How does metallography show heat treatment effects on metals? Imagine peering into a tiny universe inside a metal piece, revealing secrets about how it was treated and how it might perform. Metallography is the key to unlocking these secrets. It allows us to see how heat treatment changes the internal structure of metals at a microscopic level. When metals are heated and cooled in specific ways, their internal arrangement of atoms shifts, creating different phases and grain structures. Metallography helps us visualize these changes clearly. Heat treatment involves heating a metal to a certain temperature, holding it there for a set time, and then cooling it at a controlled rate. This process causes atoms to move around, leading to phase transformations. For example, in steel, heating can turn ferrite into austenite, and cooling can produce martensite or pearlite, depending on how fast it cools. These transformations directly impact the metal's strength, hardness, and ductility. Using a microscope, metallographers examine the microstructure of the metal after heat treatment. They look for changes in grain size, which can be refined or made coarser. Smaller grains usually mean the metal is stronger and tougher. Larger grains might make it more brittle or less durable. They also identify different phases within the metal, like pearlite, martensite, or bainite, each with unique properties. These phases appear as distinct shapes and contrasts under the microscope, helping us understand what kind of heat treatment was applied. Metallography can also reveal precipitates, tiny particles that form during heat treatment. These can strengthen the metal or sometimes cause embrittlement if they are too large or unevenly distributed. Additionally, it can show defects like microcracks or residual stresses that might have developed during cooling. These features can point to problems in the heat treatment process or indicate why a part failed. In failure analysis, metallography is like a detective's tool. It helps determine if the heat treatment was done correctly or if improper procedures caused microstructural issues. For example, if a steel part was quenched too quickly, metallography might show excessive martensite, making the metal brittle and prone to cracking. On the other hand, slow cooling might leave behind soft phases, leading to wear or deformation. In practical terms, metallography confirms whether the heat treatment achieved the desired microstructure and mechanical properties. It provides a visual record of the internal condition of the metal after treatment. This information helps engineers understand why a component failed and guides improvements in manufacturing or repair processes. By studying these microstructures, we can better predict how metals will behave and prevent future failures.